In this video, we'll explore how to use algebra to evaluate limits. We'll start with this motivating example. Suppose you want to find the limit as x approaches 2 of the function x squared minus 4 over x minus 2. If this function happened to be continuous at 2, then we could just substitute 2 for x and evaluate the limit. But we can see that the denominator is 0 when x equals 2, so 2 is not in the domain, and there's no hope of using continuity to evaluate this limit. Moreover, as x approaches 2, the numerator function also approaches 0, so we have a 0 over 0 indeterminate form. Based on the information we have at the moment, there's no way to evaluate this limit. We need to work at it a little more. And what we're going to do is we're going to use some algebra. So we'll notice that the numerator can be factored as the product of x minus 2 and x plus 2. We can cancel the factors of x minus 2 and get a simpler expression for the function. But you have to be careful. Whenever you have an equation involving variables, there's really a domain attached to that equation. In other words, there's a collection of x which make that true. Not every x may make both sides equal to each other. In this case, you're all right as long as x isn't equal to 2. Because if you try to plug 2 into the left-hand side, you'll get a 0 in the denominator. So x squared minus 4 over x minus 2 is equal to x plus 2 as long as x is not equal to 2. So if we plot the two functions, we should realize they're not the same function. The function on the left does not have 2 in its domain, while the function on the right does. So they can't possibly be the same function. However, if we ignore what happens at x equals 2, the functions are identical. There's no way to distinguish between them away from the argument 2. We're interested in the limiting behavior of the left-hand function as x approaches 2. But since the right-hand function is identical near, but not necessarily at 2, the limiting behavior will also be identical. This is the limit we wanted to evaluate in the first place, but the limit on the right-hand side is 4, using continuity of the polynomial function x plus 2. The limiting behavior has to be the same, so now we realize that the original limit we were looking for is in fact 4. This suggests a possible general strategy for analyzing a limit. Use algebra to find a new function that's identical to the original function near, but not necessarily at the argument that you're targeting. See if you can figure out the new limit, and if you can, you're in business. And the best case scenario is that the new function is actually continuous at the target argument, and then you can just substitute that argument into the new function to evaluate the limit you were originally trying to find. So let's look at some examples. Say you wanted to find the limit as x approaches 3 of this function here. Now, if this function were continuous at 3, then we could simply evaluate the function and there would be our limit. But you'll notice that 3 is not in the domain, so there's no hope of using continuity. Moreover, the denominator function approaches 0 as x approaches 3. So what we have is a 0 over 0 indeterminate form. Given the function as is, there's simply nothing we can say about the limit. We're going to have to use algebra to try to shake it loose and see if we can figure out what the limit is. So let's clear out the numerator by multiplying top and bottom by 3x. We'll distribute the 3x across the numerator, but we'll keep the denominator factored. 3 minus x and x minus 3 differ by a factor of -1. And now we can cancel these out to obtain the expression -1 over 3x. Once again, we're going to be careful about our domain. 0 is not an option, nor is 3, as it'll make the denominator 0 on the left side. So for all x except 0 and 3, this equation is true. We'll notice that the function on the right is actually continuous on the set r minus 0. In particular, it's continuous at 3, which is our target argument for the limit. That means the limit as x approaches 3 of the original function is actually equal to the limit as x approaches 3 of -1 over 3x, which is simply -1/9. Let's just be very clear about what's going on here. The function on the left, 1 over x minus 1 over 3 divided by x minus 3, is not the same function as -1 over 3x, but it's awfully close. Their values agree everywhere except at 0 and 3. 0 is not in the domain of either, and 3 is in the domain of the right-hand function but not the left. These functions in particular are going to agree in value near the argument 3, and that's all it takes to conclude that they have the same limiting value as x approaches 3. And since we can evaluate the limit of -1 over 3x as x approaches 3, we can in fact evaluate the limit of the original function as x approaches 3. Let's try this again. Here's a function whose domain does not include 0, so there's no chance of applying continuity and substituting 0 and figuring out this limit. And being careful to notice what happens in the numerator, we see that the numerator function also approaches 0 as x approaches 0. So this is a 0 over 0 indeterminate form. We can't decide what the limit is at the moment. So in this case, we're going to use a trick that you often see with radical expressions. We're going to multiply by the so-called conjugate. These two expressions here are called algebraic conjugates. The motivation for this maneuver is the following observation. Suppose you take the product of expressions p plus q and p minus q. If either p or q or both have any kind of radical expression in them, then when you look at the result, p squared minus q squared, you'll notice that any possible radical expression has been squared away. In other words, multiplying by a conjugate tends to get rid of radical expressions. Of course, you can't just multiply the numerator by the conjugate. You have to do the same thing in the denominator to keep the expression the same. Your new numerator is now the difference of these two squares, and your denominator will keep factored. We get 4 plus x minus 4 in the numerator. The 4's cancel, and now we can divide out the x's in the numerator and the denominator. And finally, we have this expression. Once again, we're going to pay careful attention to the domain. First of all, x has to be greater than or equal to -4 for either of these expressions to make sense. And of course, we can't have 0 in the original expression. This means that we have an equation valid for all x in the indicated set. The important point here is to notice that the function on the right is actually continuous at 0. Since the two functions agree near 0, they have the same limiting value. And since the right-hand function is continuous at 0, we can just substitute 0 in, and we find that the limit we were looking for is 1/4. Suppose we want to find this limit. We could naively attempt to use the sum law, but we would find that the first limit's infinity and the second limit is negative infinity. This is one of these indeterminate forms. So we're not going to be able to simply evaluate it as is. Let's use some simple algebra. In fact, we'll just add these terms together by finding the least common denominator and collecting the numerator. And so we have a new expression for the original function, which is clearly valid for all reals except 0. Therefore, these functions have the same limiting value as x approaches 0. We'll notice that the numerator approaches -1, while the denominator approaches 0 through positive values, since x to the 4th is always going to give you non-negative values. This means the limit that we're looking for is actually negative infinity. Here's an example where it's not just pure algebra, but a trig identity is going to help us. We have the limit as x approaches pi over 2 of cosine squared x over 1 minus sine x. Since sine of pi over 2 is 1, the denominator is 0 when x equals pi over 2. Pi over 2 is not in the domain of this function, and there's no chance of using continuity to evaluate the limit. And as in the previous examples, the numerator function also approaches 0 as x approaches the target argument, so we have a 0 over 0 indeterminate form. We really do need to work on this before we can evaluate it. We'll use the Pythagorean identity sine squared plus cosine squared equals 1 to rewrite the numerator as 1 minus sine squared. Factor the numerator and cancel out the like terms. We have a new expression for our original function, and we have to figure out the domain on which this is true. Sine x can't be equal to 1 lest there be a 0 in the denominator, so we need to figure out where that happens. Let's just sketch a quick graph of sine x, and we'll remember that sine of pi over 2 is equal to 1. And to find all the other arguments where sine is equal to 1, we can jump to the left or the right by 2 pi, or 4 pi, or in fact any integer multiple of 2 pi. So let's try to write this down carefully. The arguments we need to throw out are pi over 2 plus any multiple of 2 pi as long as that multiple is an integer. And we can stitch this all together with the following notation. We can use this vertical bar which reads such that. In other words, we're looking at the set of all pi over 2 plus k2 pi such that k is an integer. This gives us all the arguments where sign is equal to 1 and the denominator vanishes. In other words, the domain of this expression is all reals except for this exceptional set we just determined. The big observation is that this function is continuous on R, so we can find the limit by just substituting. In fact, the limit as x approaches pi over 2 of our original function is just the limit as x approaches pi over 2 of 1 plus sine x, which by substitution is simply 2.